So vectors in three-dimensional system, right? We have learned vectors in two-dimensional systems, right? Uh, Vectors, when we learn about the vectors in two-dimensional system, we had only x and y axis, right? So there is no difficulty in finding positive axis, right? You can take any axis as a positive and negative, right? So we learn that the unit vector along the x-axis is I and unit vector along the y-axis is j, right? So now in here, instead of the two-dimensional system, we are going to learn about the three-dimensional, the vectors in three-dimensional system, right? So instead of having two axes, x and y, now we have three axes, x, y, and z, right? So uh, when applied to solving problems in three dimensions, the operations of vector algebra are greatly simplified if the vectors are first represented in Cartesian vector form. So that's why we are going to learn this the vectors in three-dimensional systems, because if we can represent those data in three-dimensional system using vectors, it will simplify our problems, right? The first thing is that you should know how to represent the x, y, and z axes, or how to mark the x, y, and z axis. Which direction of the x axis is positive, which direction of the y axis is positive, right? Which direction of the z axis is positive, right? So here we use the rule called right-handed rule to find out which direction of the x and y and z axis are positive, right? So we in here mechanics use the right-handed rule, right? So it says that a rectangular coordinate system is said to be right-handed if the thumb of the right hand points in the direction of the positive z-axis. You can see the thumb is points in the direction of positive z-axis. Then when the right hand fingers are curled about this z-axis and directed from positive x towards the positive y, right? So you keep your thumb in the positive z-axis, then the right hand fingers are curled. If you curl your right hand fingers about the z-axis and directed from positive x toward the positive y-axis, right? So this is the positive x and this is positive y. If somebody says that I don't want to have the z in this direction, I want to have it in this direction, so this is my positive z. So what is which way my x and y axis are positive, right? So you keep your right hand thumb in this direction, right? So this is the positive z axis, right? So then this one is the positive x axis and this one is the positive y axis, right? So if someone say no, my z positive z axis in this direction, my positive z is this direction, then your positive x is here, positive y direction is here, right? So you should use the right hand uh, rule to mark the positive direction of this x, y, and z coordinates, right? This is where we use this right hand rule, right? So in our uh, two-dimensional system, we had two unit vectors I and j. Here we have three unit vectors. For x direction we have unit vector I, y direction we have unit vector j, and z direction we have unit vector k, right? So these are the important things that you should remember, right? Say this is x and this is y and this is z, right? So this is our three-dimensional coordinate Cartesian coordinate system x, y, and z, right? So now we have a vector. Say a vector, any vector may have one, two, or three rectangular components along the x, y, and z coordinate axis depending on how the vector is oriented relative to the axis, right? So if it is just along the x-axis, then it has only one rectangular component because y and z components are zero, right? Say if it is on the x z plane, say it is on the x y plane, say there is some vector in x y plane, then it has only two components. One is this component and one is this component, right? So depending on the how the vector is oriented relative to the axis, the number of rectangular components are dependent, right? So say now we have a vector in this direction. It is not in the x y z plane, it is on all these rectangular x y and z space, right? So we take vector in another color. Say we have vector in this direction. This is vector a, we represent it as vector a, right? So then this vector can be resolved into x, y, and z axes, right? Like we can write, once it resolved in x and y and z axes, we can write vector a can be resolved ax plus ay plus ac, right? So at the the vector in the vector a can be resolved into the vector in x direction plus vector in y direction plus vector in z direction. If just ax, we can also write the magnitude of the vector in x direction ax times I plus magnitude of the vector in y direction times j plus magnitude uh, of the vector in z direction times k, right? Here if you remember that I told whenever I represent a vector, I use arrow above the letter, or if it is in the printed form, use a bold letters to represent the vectors, right? So whenever also we can write as axi plus ayj plus ack, right? So this is just a scalar quantity. Since I don't have any arrowhead above this letter, so this is the magnitude of the vector in x direction. This is the magnitude of the vector in y direction, magnitude of the vector in z direction, right? So if we have a vector A, we can resolve that vector to three rectangular components: ax, ay, az, right? So sometimes this ax part can be 0, ay part can be 0, az part can be 0. It is depending on the orientation of the vector, right? So this is the general vector A, which is in the x, y, z space. So I can resolve that into three components: x, ax, ay, and az, right? So if you go to our presentation, if you take this, here the vector A can be resolved into three components as I mentioned earlier: ax plus ay plus ac, right? So ax again is the scalar quantity, right? Is the magnitude of the vector in x direction. Ay is the magnitude of the vector in y direction. Magnitude of the vector A in z direction, right? So so the magnitude of vector A can be expressed as this expression, right? The positive square root of the sum of the squares of its components, right? Ax squared plus ay squared plus az squared square root, right? Why this is? So it is very simple. If you take this is our vector A, right? So this length is ax and this length is ay, right? So what is the length of this one? This one is ax squared plus ay squared square root, right? So this is AC, and so this one also AC. Then this one is square root of ax squared plus ay squared right? So this is AC. So this is the length of A, right? The vector A. So A is equal to ax squared plus ay squared plus ac squared, right? This is right plus a this, right? So a squared is equal to this. So a is equal to ax plus ay plus az square root, right? That is how it comes here, right? So this is the magnitude of a vector in three-dimensional Cartesian coordinates, right? So then if it is a vector, we know that it should have two components. One is the magnitude, other one is the direction, right? So the direction of the vector A is given by the coordinate directional angles alpha, beta, and gamma. So alpha is the angle between the tail of the vector A and positive x-axis, and beta is the angle between tail of the vector A and positive y-axis, and gamma is the direction of vector tail of the vector A, tail of the vector, and positive c axis, right? So directional coordinate direction angles are always tail of the vector and positive axis of the respective positive axis, right? So alpha, beta, and gamma is between 0 to 180, right? So alpha, beta and gamma are between 0 and 180, right? So cos alpha we can represent it as ax divided by a, right? Cos alpha is, we can represent it ax divided by a, right? And cos beta we can represent it as ay divided by a, right? So this ax is the magnitude of the vector a in x direction, and this is the magnitude of the vector a. So this is the magnitude of the vector a in y direction, and this is magnitude of vector a. This is the magnitude of vector a in z direction, and this is the magnitude of a, right? So if we take example, let me take example, right? uh, if I take the example, so now we have a vector a is equal to 3i plus 4j plus 5k, right? So we have vector a 3i plus 4j plus 5k, right? So then what is the magnitude of the vector a? The magnitude of the vector a is equal to, this is now ax, right? And this is ay, and this is ac, right? So the magnitude of the vector is equal to 3 squared plus 4 squared plus 5 squared, right? So this is square root of 9 plus 25, right? So square root of 50, right? We, it is plus or minus 50, but we take only the positive fraction, right? So the magnitude of the vector a is equal to 3i plus 4j plus 5k. The magnitude of the vector a is 50, right? So what is the directional or angle between the x-axis and the vector a? We know cos alpha is equal to ax over a. So cos alpha is equal to, our ax is equal to 3 and a is equal to square root of 50. So alpha is equal to cos inverse 3 over square root of 50. In the same way, you can calculate the cos beta, which is equal to ay over a, right? So ay is equal to 4, right? Here you can see ay is equal to 4 divided by square root of 50, right? So beta is equal to cos inverse 4 over square root of 50, right? So in the same way, you can calculate the cos gamma, which is equal to AC over A, right? AC is equal to 5. This is square root of 50, right? So likewise, you can find out the uh, coordinate direction angles, right? So if you are given any vector which is in the xyz plane, xyz space, then you can find the magnitude of the vector and the coordinate direction angles, right? So when you have a vector in x, y and z space, if you want to define that vector, you should give the magnitude and the coordinate, direction, angles. Then only you can define the vector, right? Okay, so now you want to add two vectors, vector A and vector B. So what do is when you add vectors, you add the items together. You can write the vector A as AXI plus AYJ plus ACK. In the same way, you can write the vector B as BXI plus BYJ plus BZK, right? So you take the items together. So you take I out, you can write AX plus BX. You take the y terms, j terms together, you can write AY plus BYJ. Then you take the k terms together, you will get this, right? So this is how you can add two vectors in three-dimensional space. Why this addition is important? Because if you want to find out the resultant force, we add two vectors to find out the resultant force, right? So you can generalize that. If you want to find out the resultant force of n number of vectors, you can say you just add those forces, right? So which means that you add the I terms together, you add the j terms together, you add the k terms together, right? I terms sigma fx, and this is sigma fy and sigma fc, right? So this is how you find the resultant force when you have more two or more than two forces, right? So we'll look into the example, then you will get familiarized with these concepts. Okay, we'll look at the example. Okay, two forces act on the hook shown in figure, right? So there is a hook that there are two forces act on the hook, right? Force F1 and F2. If you take the force F1, the magnitude is given and the directional angles are given, right? Specify the magnitude of F2 and its coordinate direction angle so that the resultant force Fr acts along the positive y-axis and has a magnitude of 800 Newton, right? So we have two forces. Force F1, we know the magnitude and coordinate direction angles. Force F2, we don't know the magnitude and the direction angle. That is what we need to find. And question says the resultant forces acts along the positive y-axis. Fr, which is the magnitude of the Fr, is equal to 800 Newton, right? So we want to determine the magnitude of the F2 and the coordinate direction angles. So how can we solve this? We know the Fr force, we take this Fr force. So this is the system, right? We know force Fr, resultant force, is equal to addition of F1 plus F2 force, right? So if we add the vectors, so So these are vector additions, right? Not just algebraic addition. The summation of vectors is equal to of the force F1 and F2 is equal to resultant force, right? So our vector, the if I express Fr in Cartesian vector notations, we know Fr force is in the y direction, right? So the magnitude is 800 Newton. So I can write Fr force is equal to, there is no component in x direction, so 0 I plus the y direction, it is 800 j, right? Plus there is no component in c direction, so 0 k. So I can write as 800 j, right? The resultant force, if I express it in Cartesian vector notation, which is equal to 800 j, right? So if I express the vector f1 in Cartesian vector notation, how can I express? My force F1 is 300 magnitude, right? So what is the projection in x direction? 300 cos 45. Angle is 45, right? Angle between the positive x-axis and the tail of the vector is 45. Then the unit vector I, right, plus the projection of this vector in y direction is 300. Angle between the tail and the positive y direction is 60 degrees. So 300 cos 60 times j plus the angle between the F1 and positive z-axis is 120. So it is 300 cos 120 k, right? So then, so if I simplify this expression, I will get 300 cos 45, I will get 212.1 I plus 300 cos 60, 150 j, and 300 cos 120. Cos 120 is minus half, so it is minus 100, 150 k, right? So this is force F1. So we know from our initial expression, Fr is equal to F1 plus F2, right? So I write F2 force also in ijk terms. So I write F2 force equal to F2xi plus F2yj plus F2zk, right? F2x means projection of the F2 force in x direction. That is the magnitude, right? So F2y means projection of F2 force in y direction. F2z means projection of F2 force in c direction, right? So I, j, k are unit vectors along x, y and c directions, right? So if I put into this expression, here Fr is 800 j, right, which is equal to F1 is 212 I plus 150 J minus 150 K plus F2x I, right, plus F2y J plus F2z K. So I take the I terms together, 212.1 plus F2x I, right? Then I take the J terms together, 150 plus F2y J. I take the K terms together, so it is minus 150 and F2z, right? So F2z minus 150 K, right? So I took the I terms together here. What are the I terms here? This one and this one, right? So 212 plus 1, 212.1 plus F2x. So what are the K terms? J terms? This one and this one. So I took 150 plus F2y times J. So I take the K terms together. What are the K terms here? This one and this one, right? Since this is minus, it goes here. This is plus F2z minus 150, right? So which is equal to 800 J, right? So from here we can say here items, what is the value of items is 0, right? So if we compare the items, then this side it is 0, which is equal to 212.1 plus F2x, right? So if I compare the J terms, then here value is 800, which is equal to 150 plus F2y. So if I compare the K terms, then here no K terms, which means value of the K terms in the left hand side is 0, right? Which is equal to F, which is equal to F2z minus 150, right? So why it is like this? We know the resultant force is equal to the vector summation of force F1 and force F2. Our resultant force is in y direction, right? So which means the components in z and x axis are 0, right? It is in the y direction. So we can express our vector resultant force as in Cartesian notation as 800 J. So our forces F1 and F2. Our force F1 is this and force F2 we don't know. We express like this, right? So the summation of these vector summation of these two forces should equal to the resultant force, right? If you take the resultant force, I terms in the resultant force is 0. So if this one to be 0, then if I terms in this term should be is 0, the I terms in this one in this side should also be 0. So which means 0 should be equal to 212.1 plus F2x, right? The resultant force, J terms in the resultant force is equal to 800. So which means that The j terms in the vector summation of these two should also be equal to 800, right? So 150 plus f2y is equal to 800. The k terms in the resultant force is 0. So this, if these two are equal, then this one should also be equal to 0, right? From here we can say f2x is equal to minus 212.1 and f2y is equal to 650 and f2z is equal to 150, right? So from this you can find the magnitude of the F2 force. F2 force magnitude is equal to square root of F2x squared plus F2y squared plus F2z squared, right? So which means 212 minus 0.1 squared plus 650 squared plus 150 squared, right? So here, which is equal to 700 Newton, right? So this is the magnitude of the F2 force, right? So the magnitude, then we can find the direction, coordinate direction angles, right? So cos alpha or the angle between the tail of the vector and positive y direction, we call cos alpha is equal to ax by a, right? In our according to our previous slide, cos alpha is equal to ax by a. Here f2x over f2 force, f2x is minus 212.1 divided by 700, right? So if you take this, you will take the inverse of cosine, you will get alpha is equal to 108 degrees. So say cos beta is equal to f2y divided by f2. f2y in here is equal to 650 divided by 700, which is equal to beta is equal to 21.8 degrees. The same way, cos gamma is equal to f2z divided by f2 is 150 divided by 700. So gamma 2 is equal to 77.6 degrees, right? So likewise you can find any force in the xyz space, right? So here I have put the solution of this example, so you can follow this, right? So basic rule is that the summation of two forces is equal to the vector summation of two forces are equal to the resultant force of that two forces, right? There is one more very important concept, unit vector. Unit vector is a vector having magnitude of 1. Okay, unit vector is a vector which has a magnitude of 1. So if we take those the Cartesian axes x, y, and z, we learn that the unit vector in x direction is I, vector in y direction is j, unit vector in z direction is k, right? So I, j, and k are unit vectors, which means the magnitude of the unit vector I is equal to 1, or j is equal to 1, and k is equal to 1, right? So unit vector is a vector which has a magnitude of 1, right? So now we know x direction we have the unit vector I, y direction unit vector is j, and z direction unit vector is k, right? So if we have say that if we have a vector in this direction, if we know the magnitude of vector in x direction, say the magnitude is 2, there is a vector in x direction, the magnitude is 2, we can express the vector, say vector A is equal to 12i, right? So if we know the magnitude and we know the unit vector in that direction, so we can express the vector using unit vector. But say that we have a vector in this direction, so then we cannot express this vector just using unit vector I only, or j only, or k only, right? So then if we can find the unit vector in this direction, then we can express, if we know the magnitude of this, say this is b, this b vector, if we know the magnitude of the vector b, then we can express this b vector using this magnitude and unit vector along this direction, right? So that is the importance of the unit vector, right? So say, as according to our definition, unit vector is the vector which has a magnitude of 1. So then we say, say so this is x and y and z. So we have vector, a. So a we can express like this. A can be expressed as vector a is equal to ax I plus ayj plus ack, right? So what is the magnitude of a? Magnitude of a is equal to ax plus ay plus ac square root, right? So this is the magnitude of vector a, right? So what is the unit vector in this direction, in the direction of vector a? What is the unit vector in the direction of vector a? We define unit vector as u. So unit vector in the direction of a is equal to, from the definition we know unit vector is a vector which has a magnitude of 1, right? So then if the vector a is divided by its magnitude, then we say it is the unit vector in a direction. If any vector divided by its magnitude, we call it as the unit vector in the direction of that vector. So if we take here Here, if we divide any vector, say A is a general vector, right? Divided by its magnitude, will it give the unit vector? Say A, we know it is AX plus AXI plus AYJ plus ACK. Then we divide this by the magnitude of the A, which is AX squared plus AZ squared, right? So if we take this, so what is the magnitude of this one then? Then magnitude of this one is AX squared divided by AX squared plus AY squared plus AZ squared, right? Plus AY squared divided by AX squared plus AY squared plus C squared, right? Plus AC squared divided by AC squared, right? Then you take the magnitude, right? So this denominator and numerator is cancelled out and you will get square root of 1, so which is equal to 1. So the magnitude of this vector is equal to 1. So that's why it is a unit vector. So if we take any vector divided by its magnitude, then we can call it as a unit vector in that direction, right? So if we take any vector, then divided by its magnitude of the vector, it is the unit vector, the unit vector in the direction of the vector, right? So we use U to demonstrate or define the unit vector or represent the unit vector, right? So if you, so we know that now unit vector, say U a unit vector in this direction is equal to any vector divided by its magnitude, right? So any vector divided by its magnitude we call as a unit vector, right? So I can express this as AXI plus AYJ ACK divided by vector, the magnitude of the vector A. So if I express like this, AX over A times I plus over A times J plus AC over A times K. So then what is this AX over A? We learn that it is the cos alpha, right? In our directional cosines or direction cosines or coordinate direction angles, we learn that cos alpha is equal to AX over A, right? So this is cos alpha, which means that angle between the tail of the vector A and the positive x direction, right? Then plus ay over a is ay over a is cos beta times j, right? Beta means angle between the tail of vector A and positive y direction, plus AC over A means cos gamma k, right? So unit vector can be expressed as in this way also, using the direction cosines, right? If you know the angles, then if you know the direction cosines of any vector, you can use those direction cosines and express the unit vector in this way also, right? There is one more important relationship, right? We know that the unit vector has the magnitude of the unit vector is equal to 1, right? So magnitude of the unit vector is equal to, this is part square plus this part square plus this part square root is equal to 1, right? So cos squared alpha plus, if I say like this, say cos alpha squared plus cos beta squared plus cos gamma squared, square root is equal to 1, and if I remove this square root, still this one is equal to 1, right? So cos alpha squared means cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1, right? So then what is the importance of this relationship? If you know two direction cosines, then you can find out the other direction cosine using this relationship, right? So this relationships only true for unit vectors, right? This is only true for unit vectors, right? So if you want to find the direction cosine of a unit vector, then you can use this direction cos this one to find the other direction cosine, right? So we'll use this concept, unit vector concept, in coming examples. Then you can see how we can use or how we can apply this unit vector concept in our mechanics class. Position vectors. Position vectors are important in formulating a Cartesian force vector directed between 2 points in space. Position vector we designated using R, okay, we designated using R, is defined as a fixed vector which locates a point in space relative to another point, right? So say for example, say that if R extend from the origin of coordinates O to point P, X, Y and Z, having coordinate of X, Y and Z, then R can be expressed in Cartesian vector form as R is equal to, vector R is equal to x times I plus y times j plus z times k, right? If I say again, if R extend from the origin, so this is the origin of coordinates O to point P, which has a coordinates of x, y and z, then R, the position vector R, can be expressed as xi plus yj plus zk, right? So as we mentioned, position vector is a vector which locates the point relative to another point, right? Here the point, this position vector r locates the point P relative to the origin O, right? So say now, so any, so what actually position vector means, that say now you want to move to the P, right? Starting from origin. So how can you approach to point P? Position vector tells you should move x distance in I direction or x direction, then y distance in the vector z direction, which means in y direction, and move z distance in vector k direction, which means z direction. Then you can come to the point P, right? So it tells you how to reach a point in this Cartesian coordinate system, right? So R is a position vector which we can express as R is equal to xi plus yj plus zk, right? So now say you want to define a vector. In more general cases, say that you want to find out the position vector relative to point A. You want to express the point P relative to point A, not relative to the origin. Then how can you express this? How can you find this position vector, right? So we, from the head to tail vector addition, we know that, or the vector triangle method, we know from here we can write as RP, vector RP is equal to RA plus R, right? So RB means the position vector of point B relative to the origin. This is, say, this is the origin O, right? RA means position vector of point A relative to the origin, and R is the position vector of point B relative to the point A, right? So RB, we know that coordinates of B is XB, YB and ZP. So RB can be expressed as XBI times YBJ times ZBK, right? And RA can be expressed as, if I write here, XA times I plus YA times J plus CA times K, alright? So then what is the vector R? Vector R is equal to RB vector minus RA vector, right? So vector subtraction. So this is the vector RB and this is the vector RA. From that, so this is vector RB, this is RA, right? This is RB vector and this is RA vector. So you take the I terms together, you will get XB minus XA, and you take the J terms together, you will get YB minus YA, and K terms together, ZB minus CA, right? So if you want to express any point relative to the another points, so you can express the position vector by just subtracting the points that we want to express you should subtract the points which is relative, right? Then use the Cartesian unit vectors I, j and k, right? So any pair, any point in this xy is a Cartesian coordinate system, you can express relative to other point, right? So these position vectors we are very important. In the coming slides we are going to do some example. There you can see how can we use these position vectors to solve problems, right? Okay, now let's see some example to get familiarized with the concepts that we have learned about unit vectors and position vectors, right? In this example, it says that an elastic rubber band is attached to points A and B, right? The point A and point B, the rubber band is attached as shown in this figure, right? So we are asked to determine the length of the rubber band and the direction measured from A towards B. So we are asked to find the length of the rubber band and the direction, right? So now how can we do this type of problem, right? There might be many ways, but we can use the concept position vector and unit vector. Let's see how we can solve this type of question, right? Here, if you take this, uh, if we can find the position vector from A to B, or we can find the vector AB, then we can find the magnitude of the vector AB. If we find the magnitude of the vector, which means that is the length of the rubber band, right? So if we take A, what are the coordinates of A? Coordinates of A, you can see that A is on the x z plane, right? So the coordinates of points A, the A is on xz plane, right? You can see A is 1 meter from the origin in x-axis and 3 meters down from the z-axis, right? So this is positive z direction, positive x direction, and this is positive y direction, right? That is where our right-handed coordinate system, right? So A, can see it is 1 meter from the origin towards x-axis, and since it is on xz plane, y coordinates is equal to 0 and z coordinates is equal to -3. Why? This is positive x-axis, right, in this way. So this one is -3 meters in negative z direction, right? So what is the coordinate of B? Point B. If we take the points B, coordinates of point B is, it is -2 in x-axis, right? -2, you can see this is our origin, right? You should go 2 meters from origin in minus x direction, right? Then in y direction you should come 3 meters, in positive y direct. Actually it is 2 meters in positive, here 2 meters in positive y direction, right? And 3 meters in positive z direction. So coordinate of point B is -2, 2 and 3. Now we want to find the AB vector, right? We want to find the vector AB, or we say position vector of B relative to A, which is that now we want to find this vector, right? So when we want to find this vector, we should reduce the head's coordinate, reduce the tail coordinate from the coordinates of the head, right? So this is our head coordinates and this is our tail coordinates, right? So head coordinates is -2, 2 and 3, minus 1, 0, -3, right? This is our tail coordinates, right? So then if I write in IJK form, minus, so I can write this as -2i plus 2j plus 3k minus this one is I 1i plus 0j, which means 0, and minus 3k, right? So if I take I terms together, get -2 minus 1 times I plus, if I take j terms together, 2 minus 0 times j plus 3 k terms together, right? 3 minus 3 times k, right? So which means that minus 3i plus 2j plus 6k. This is the vector AB, right? So if we find the magnitude of this vector, then we can say that is equal to the length of the rubber band, right? So the magnitude of this vector, we can say RAB, this vector RAB, the magnitude, we can say RAB magnitude is equal to square root of -3 squared plus 2 squared plus 6 squared, right? So this is equal to square root of 9 plus 4 plus 36, which is 49. So the magnitude of the vector RAB is equal to 7 meters, right? So the length of the rubber band, length of this rubber band is 7 meters, right? Now we want to find the direction of the vectors, right? So if we find the unit vector along this one, we can say the direction, right? So what is the unit vector along the AB? We say it is UAB. If we find the what is the UAB, then vector AB divided by the magnitude of the vector AB, right? So vector AB is equal to -3i plus 2j plus 6k. Magnitude of the vector is 7, right? So then we can say UAB is equal to minus 3 over 7 I plus over 7 times J plus 6 over 7 K, right? But we know from our previous slides, previous knowledge, UAB, any unit vector we can express as cos alpha I plus cos beta j plus cos gamma k, right? So if so, then cos alpha I is equal to this, right? So we can say cos alpha is equal to minus 3 over 7 and cos beta is equal to 2 over 7 and cos gamma is equal to 6 over 7, right? From this you can say alpha is equal to 150 degrees and beta is equal to 73.4 degrees and gamma is equal to 31.0 degrees, right? So now you know alpha, beta and gamma, right? So we know this alpha means it's the direction cosine. Cos alpha is the direction cosine, right, of the tail of the vector and the positive x direction, right? So if take this, so this is the positive x direction and this is the z direction and this is positive y direction, right? So this angle is 115 and beta is 73.4, right? Angle between the tail and positive y direction, this one is equal to 73.4 and this angle is equal to 31 degrees, right? So you can see that now using the unit vector concept and the position vector concept, we can easily solve this type of problem, right? So I mentioned that in our previous slide, our position vector tells us how to move from one, I mean relative one position to the other one, right? So we want to find the position, relative position of B relative to the A, right? So which tells us that how you should move from A to B, right? So in here you can see that in order to move from A to B along the x-axis you should travel -3 distance, right? From here you should travel -3 distance in x-axis, along the x-axis, then +2 distance in along the y-axis, then travel 6 meters along the z-axis to reach the point B, right? So that is the position vector, right? So this is how we can use the position vector concept and unit vector concept to solve this type of problems, right? So we are going to use this concept in mechanics. Still not we are applying this concept in mechanics just to find the force. Here we use these concepts, but in coming lectures we use all these concepts in mechanics problems. The second question, it says the man shown in figure pulls on the cord with a force of 70 lb. Represent this force acting on support A as a Cartesian vector and determine its direction, right? So now man pulls the cord, right? So the cord is in A B direction, right? So man pulls that cord, which means that force inserted by man on this cord is also in A B direction, right? So the force is in this direction, right? Force created by man is in this direction, right? So we know the magnitude of the force is 70, and we are asked to put the force in Cartesian vector notation and determine the direction, right? So if we express this force in Cartesian vector notation, how can we do? We know the magnitude, right? So if we find the unit vector along this direction, then we can express the force F in Cartesian vector form, right? So if we know, say that if some force is on x direction, say this is x direction and this is y direction. If some force in x direction, say it is 80 lb, if we ask to put in Cartesian notation, we can say it is 80 I, right? If it is in y direction, say it is 80, then we can say it is 80 j, right? Since we know the unit vector in x direction is I, we can simply multiply it by the unit vector, the magnitude of the force by unit vector, then we can get the Cartesian vector form, right? But so in here also, if we find the unit vector along AB direction, then we can express this force in Cartesian vector form, right? Say uh, then if we know the unit vector in this direction, we can find out what are the directions of this force, right? So then we should find out the unit vector in AB direction. So how can we find out the unit vector? If we know the vector AB, then we can divide the vector AB by its magnitude, then we can find out the unit vector in AB direction, right? Can we find the vector AB? Yes, right? Because we are given the coordinates of A and B, right? So we can find out the coordinates of A and B, then we can find the unit vector in AB direction, right? So let's see how can we find the unit vector in A, B direction, right? The coordinates of A is equal to, can see that A is on the Z axis, right? So which means that X coordinate is 0, Y coordinate is 0 and Z coordinate is 30, right? Since say this is the origin, say let's take this as our origin. Let's take this as our origin point. So this is O, then this one is 60. So this point is 24, right? So this is 24, right? So if I put in Cartesian vector form, I can write this as 0I plus 0j plus 24k, right? So which means it is 24k, right? So what is coordinates of B? B is, you can see it is 12 in x direction, right? 12 in positive x direction and minus 8 in minus 8 in positive negative y direction, and z coordinates is 0, right? So then if I put this in the Cartesian vector form, it is 12i, it is 12i, right, minus 12i minus 8j plus 0k, right? So then these are vectors, right? So then what is the AB vector? What is the vector AB? Or we can say it is the position vector of B corresponding to the position of A. Then what is the AB vector? Now the head is here and the tail is here, right? So you should subtract tail's coordinate from head's coordinate, right? So it is 12i minus 8j minus 24k, right? So we'll get AB vector as 12i minus 8j minus 24k, right? So this is the position vector of the RAB or vector AB, right? So how can we take the unit vector along the AB direction? Unit vector along the AB direction is equal to AB vector divided by the magnitude of AB. What is the magnitude of AB? Which is equal to square root of 12 squared plus minus 8 squared plus minus 24 squared, right? So which is equal to 28, right? So then UAB is equal to 12i divided by 28 minus 8j divided by 28 minus 24 divided by 28k, right? So this is the unit vector along the AB direction, right? So now we know that the magnitude of the force is 70. So we can express force is equal to 70 times UAB, right? So which is equal to 70 times our unit vector in AB direction, which is 28i, the 12i, right? 12i divided by 28 minus 8j divided by 28 minus k divided by 28, right? So this one is equal to 30i minus 20j minus 60k, right? So if we express the force in Cartesian vector form, you will get something like this, right? So we know from our previous knowledge, if we take the unit vector, we can express the unit vector as cos alpha I plus cos beta j plus cos gamma k, right? So if we take the items, cos alpha is equal to 12 over 28, right? So you can take the alpha from here, which is equal to 64.6 degrees, right? Then cos beta is equal to minus 8 over 28, right? Which is, take, we can say beta is equal to minus 8 over 28, which is 107 degrees. Then cos gamma is equal to minus 24 over 28, which is equal to, you can say gamma is equal to 149 degrees, right? So we have expressed our force F in terms of Cartesian vector form as well as the directional cosines, and we show from the directional cosines we found out the directions of the force, right?